This is problem 8-59E. It's on page 449. The shape in figure P859 is to be made by gluing the flat plate to the hat section. If the beam made from this section is subjected to a shearing force of 1,200 pounds, compute the shear flow at the joint. What must be the shearing strength of the glue in PSI? Okay. All right, I'll refer you to the figure on page 449. I'll not draw it again. Notice what we're really trying to do is calculate the shear flow. We want the shear flow at the joint, which is only, what, 0.2 inches above the bottom. And you know what, I guess I should draw it so that I can point to it. So the part they're calling the hat section, they call it that because even though it's actually an extruded channel, it looks like a top hat that's been cut in half. And then there's the bottom plate. And the area we're really interested in is the area where the two pieces are connected together with glue. Okay. So despite my imperfect drawing, there's supposed to be a minimum gap there, or minimal gap there. And we're supposed to figure out how strong the glue has to be based on the shear flow. All right, so the first thing I did is calculate the shear flow Q as V capital Q over I. Now the difference between these two, capital Q is an area property, whereas lowercase q is a force per length. So it's more like a stress than it is an area property. Okay, so I don't know why they used upper and lowercase q for it, but that's what they did. Now, in Excel, I went ahead and I broke up the areas into several parts. This first area is just that very bottom rectangular area. And then I broke it up into an area, do it in green, I guess, like this on both sides. Oops, that. And then another area like this on both sides. Or, yeah. Trying to remember how I broke it up, and then that area at the top. So you'll notice that the lines 2 and 3 are the same because they're dealing with the flanges, the bottom flanges of the hat. Lines 4 and 5 are the same because they're dealing with the vertical uprights, and then line 6 is the very top plate section. So I just broke it up this way and calculated the area moment of inertia with the spreadsheet that I gave you guys, and you can see it comes out here. I'll write it on the board just for the sake of the video, but of course you can download the spreadsheet as well on the Blackboard site. Anyway, that came out to 0.367178. May as well write them all down since I had Excel calculated. And then the average position, or the centroid, came out to 0.533019 inches. Now, what is the centroid again? Well, the centroid is just how far up from the bottom is the balance point. So let's see, if this is 0.2, the thickness of the flanges is 0.1 typical. Well, then I guess 0.5 is somewhere up here. Okay, so there's capital Y bar. You have to be careful here because when you calculate Q, Q is equal to a particular area multiplied by another Y bar, but these are two different Y bars. The capital Y bar is the centroid of the overall area, whereas the lowercase y bar, what is that? Well, that's the centroid of this particular area. Okay, now what are we talking about there? Well, what we're talking about is that we're interested in the shear flow here. So we better calculate the area, or the cross-sectional property, the geometry property, at this line. Okay, so this is our axis of interest that your author talked about when he talked about the Q, capital Q. Okay, so what we need is the distance from the centroid to that line. That's what little y is. Okay, so don't be confused between those two. Little y is that distance. So what's the particular area? This. Because remember, the particular area is the area beyond the axis of interest. Okay. So what I did is I went ahead and just calculated that area, and then multiplied that by this distance y bar and came up with Q. And I did all that in the spreadsheet just to make my life easy. Okay, so there's capital Q. Now, by the way, did you know that if you were to consider the opposite side, you'd get the same result? Which is kind of interesting. But anyway, so there's Q, and it's on the spreadsheet, and I'll write it down here as well. Let's see, it comes out as about 0.3463 cubic inches. And so then we can calculate the shear flow Q. All we need is the actual shear force that's being applied, and that was given in the problem statement. In fact, that was given as 1,200 pounds. So you'll see in the spreadsheet, I just went ahead and put everything in here. Let me highlight that cell so you can see the equation I used and see that it is in fact the shear flow equation up here. So it's 1,200 pounds. Then I reference the capital Q and I, the area properties in the spreadsheet, just to make it easy. And so that comes out to about 1132 or so. And the units are pounds force per inch. Okay. And so then I could calculate the amount of shear at the cross section. Now, why would I want that? Well, the glue that's in between here has to support a shear load, right? And so basically all I really need is the shear stress between these faces here, right here and here. And so that would be, whatever that shear is, that's the amount of shear that the glue has to support and not fail under. So I just calculated that next as Q, divided by T. And so that's 1131.9 pounds force per inch. And then T, what is T? Well, that's the width along this line. Well, how much width is there? Well, there's two of these, right? And the legs over here is 0.6, the thickness here is 0.1, and so in total there's 0.7 over here and 0.7 over here, so 1.4 inches in total length there. Okay. So anyway, this came out to 808 psi or so. So the glue has to support at least 808 psi of shear load. Does that make sense? Any questions? Now that didn't really seem fair because I started off the discussion talking about fasteners. Yes?
Was V the 1,200 pounds force?
V is the shear load, the 1,200 pounds force. Yes, sir. Good question. Anything else?